all, myself Srivani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So in the today's lecture, we are going to discuss about one most important topic related to the transmission lines in electromagnetic waves and the transmission lines as here single stub matching. It is one of the impedance matching technique. So in the previous lectures, we have discussed different cases of impedance matching techniques. Now, this is the continuation part of that one as the second classification related to the impedance matching as stub matching. There are two types of stub matching techniques are available. One is single stub matching and the second one is double stub matching techniques. These are all examples for impedance matching techniques. So in the previous lecture, we have discussed what is the need for impedance matching, what are the different advantages of this impedance matching, then different types of wavelengths. From that wavelength lines of the transmission lines, we have been evaluated the relations between input impedances versus characteristic impedance along with the load impedances we have been evaluated in the previous lectures. Now we can use here the impedance input impedance relation whether it is related to the lossy transmission line or a lossless transmission line depending upon the stub we are going to use, then we'll consider the lossless or a type of lossy input impedance transmission line equation. Then from that we are going to derive stub lengths and thicknesses of a single stub matching technique. Now we are going to discuss the particular topic in this one is single stub matching. So before going to evaluate the mathematical equations related to this single stub matching, let me introduce first what actually stub, how many types of stub matching techniques are there, what are the advantages of this stub matching, then we'll move on to the mathematical analysis part. So first, a stub is a short circuited section of a transmission line connected in parallel to the main transmission line. So basically transmission line means it is a two conductor guiding structure. See, basically it consisting of two structures, two conductors as line 1 and line 2. In between we are going to add one stub. This is the connection called stub connection. Right? So basically the transmission line is a two conducting guided structure which is having two parallel wires. So those two wires are two conductors, means a stub is a short circuited section of a transmission line connected in parallel to the main transmission line. So the parallel connection which is exist between the simple transmission line is said to be extra patch is said to be a stub. So a stub is a short circuited section of a transmission line which is connected parallel to the main transmission line. And a stub of appropriate length is placed at some distance from the load such that the impedance seen beyond the stub is equal to the characteristic impedance. Means in order to equate this load impedance to the characteristic impedance, we need a stub and that is connected in parallel to the main transmission line. Right? So stub is appropriate length is placed at some distance from the load section and based upon this we can equate the load impedance to the characteristic impedance Z0. Then impedance matching. So here also we are going to match the impedance. Now use of this impedance match in order to reduce reflections from one medium to the another medium and in order to equate the impedance which is connected at the source to the destination, we use impedance matching technique. So impedance matching is one of the important aspects of the high frequency circuit analysis. So now here we are using circuit analysis, means there is source to end, there must be exist a physical connection. So impedance matching is one of the important aspects of the high frequency circuit analysis, and here we are going to use UHF lines of frequency or RF lines of the frequency. Right? Range of this UHF frequencies will be 300 megahertz to 3 gigahertz. That's why these are all called high frequency structures, right? So impedance matching is one of the important aspects of high frequency circuit analysis. And to avoid reflections, for maximum power transfer, the circuits have to be impedance matched. The main advantage of this impedance matching is in order to avoid reflections in the same medium and in order to get maximum power transfer, we use here impedance matching. Right? So to avoid reflections and for maximum power transfer, the circuits have to be impedance matched. Then transmission line sections can be used for the purpose of impedance matching. And mainly here we are using a second type of impedance matching techniques called stub matching techniques. Now, what do you mean by stub matching? So stub matching is a section of a transmission line can be used as a matching section by inserting them between load and the source. So the stub is connected between the source to the load and a small section of the connection which is connected to the parallel to that main transmission line, then the simple connection is said to be here stub. It is also possible to connect sections of open or short circuited line called stub. So here stubs are connected in two ways. One is with respect to the open connection as well as the another one with respect to the short. So it is also possible to connect sections of open or short circuited line called stub in shunt with the main line at some point or points to affect impedance matching. Right? So now what are the different advantages of this stub matching? Then the length and the characteristic impedance of the line remains the unaltered. So in order to add extra patch to that for main transmission line, that's length of the transmission line and characteristic impedance won't change. Right? That's why the length and the characteristic impedance of the transmission line L, length of the line and remains unaltered. Means length and this characteristic impedance won't be changed by adding this stub matching. This is the main advantage of this stub matching technique. Next one is from mechanical standpoint, adjustable susceptance and added in shunt with the line. So in order to adjust from point to point or from source to the destination, there is a mechanical standpoint and it is to be adjustable one. With the help of this susceptance means it is also called as sensitive. So adjustable susceptance and these are added to be in shunt connections. Shunt connections means parallel connections. So this parallelly we are going to add one simple patch section to the source to the destination of a main transmission line, and the simple process is called stub matching, right? So there are two main advantages of this stub matching. So with the help of this stub matching, the length of the transmission line and the characteristic impedance of the transmission line won't change, and the mechanical standpoint is available in order to adjust susceptance, and these are to be added up with shunt with the transmission line, right? So without affecting any changes, we just added to the extra patch section which is parallel to that of main transmission line, and the process is said to be stub matching, and extra patch we are adding to that transmission line is called stub, right? So there are two types of stub matching techniques are there. Stub matching. Under this there are two cases are there: single stub matching and double stub matching. Single stub matching and double stub matching, right? So if you are going to add one single patch in between the two transmission lines, then it is said to be single stub matching. Then in order to eliminate which are the some of the drawbacks which are exist in the single stub matching, in order to overcome that, we are going to add extra patch to that of a main transmission line, then that is called double stub matchings. Okay, so in this lecture we are going to discuss about single stub matching technique. So here is the diagram for the single stub matching. So if you observe the source voltage which is connected at the input side, and the Z0 is connected is also at the input side, means this Z0 is sometimes called as source impedance as ZS, right? So voltage and source Z0 are connected at the input side, and these are the two main transmission lines, this one and this is the two main transmission lines. One extra patch which is added between the source to the destination in between the two parallel lines, and this is called stub. So the length of this one is given by ls, means the stub length, and at the load we just added one impedance term is called zl, right? So the length from this stub to the load impedance which is connected at the output side is called given by the length l1, right? So in the same way, see, if you're going to analyze the stub length, see, this is the length which is given by L, and depending upon the real and imaginary terms, now we are going to derive the mathematical equation for the stub length and thickness of the stub. Okay, so here is the simple diagram for the single stub matching. There we have used only one single stub which is connected. See, this rectangular or square type waveform, rectangular type patch is added between the two parallel lines, and this is the connection called stub, right? So length of this one is given by ls, and we can estimate this ls with the help of mathematical equation, right? So this is the a simple stub matching diagram. So a stub is a short circuited section of a transmission line. Simply, stub means it is a short circuited section. Short circuited means parallelly we can connect between source and the destination. So it is a short circuited section of a transmission line connected in parallel to the main transmission lines. So as we have seen in the previous means introduction to stub matching's case, now a stub is a short circuited section of a transmission line which is connected in parallel to the main transmission line, and it is a means a stub of appropriate length is placed at some distance from the load such that the impedance seen beyond the stub is equal to the characteristic impedance. Means before that we are adding the characteristic impedance as Z0 here. If you place after this stub also the impedance near to this stub also, it must be equal to Z0, right? So based upon this we are going to compare the characteristic impedance and the load impedance must be equal in this particular matching case, right? Single stub matching. So suppose if we have a load impedance connected to a transmission line with characteristic impedance. See here, see, this is Z0 which is connected near to the load impedance, and based upon this the objective is here is that no reflection should be seen by the generator. Why we have connected the stub which is nearer to the load impedance, means in order to avoid reflections from the same medium, right? So suppose that we have a load impedance which is connected at the transmission line with the characteristic impedance. To avoid the reflections, we just added the stub to the nearer to that of load impedance. Then conceptually, this can be achieved by adding a stub to the main line such that the reflected wave from the short circuited end of the stub and the reflected wave from the load on the main line completely cancel each other at point B to give no net reflected wave beyond point B towards the generator. Now the use of stub which is connected nearer to the load is based upon this, and we will understand clearly. Next, consider a transmission line having a characteristic admittance. So, previously in the previous lectures, we have been evaluated load impedance as ZL, characteristic impedance as Z0, and source impedance as ZS, right? So, depending and along with that, input impedance is Zin. So, impedances cases, we just use all the notations as Z is the common notation for impedance is the generally represented with Z, hence ZL, Z0, ZS, Zin. So depending upon the substitutes, means L for load, 0 for characteristic impedance, and S for source, followed by IN is for input impedance. Now depending upon all these notations, now in order to analyze in the stub matching techniques, it is easy to analyze all such impedances with respect to the admittances. Why? Because we are adding stub in parallel to the normal transmission line. Parallel connections case, we are analyzing that one with respect to the admittances. Why? Because now to add up or now to multiply in the case of admittances only it is easy. That's why all the impedance terms are replaced by admittances in the case of this stub matching techniques. So consider a transmission line which is having a characteristic admittance. Previously what characteristic impedance means Z0 and it is replaced by characteristic admittance. Means Z0 is equal to 1 by Y0. Z0 is the notation for characteristic impedance and Y0 is the notation for the characteristic admittance. As we know that impedance and the admittance both are reciprocal to the each other, Z is equal to 1 by I, Y or Y equal to 1 by Z, neither nature. Now depending upon that, we are using the notations for the character in place of characteristic impedance Z0 as characteristic admittance as Y0 and terminates in a pure conductance as YR. So previously what we have used ZR means that is represented with a normal conductance means G. Now we are replacing with admittances, hence we are using the notation as Y suffix R, pure conductance. Since we connect the stub in parallel with the main line, it is easier to deal with the admittances as they can be added up, right? So in order to add all the admittances, then we are going to use their reciprocal terms. Hence, we are considering in place of impedances by admittances in order to analyze the mathematical equation in easy way. Then, the principal element of this single stub matching is a short circuited section of the line whose open end is connected to the line at a particular distance from the load end. Means as we have seen in the diagram, the stub is connected nearer to that of load impedance to reduce reflections in the transmission line. Right? So based upon that, the principal element of this single stub matching is a short circuited section of the transmission line whose open end is connected to the line at a particular distance from the load end. Then the input impedance at open end of stub is equal to the chosen admittance of the line. Means input impedance is replaced by here related to the admittance term as 1 by Yn, or Yn is equal to 1 by Zn. Right? So Zn is the notation for the input impedance and Yn is the notation for the input admittance. Then single stub matching is that the stub when placed at a suitable point from the load side provides a susceptance which is equal but opposite in sign to the input susceptance at the point of attachment is 0. So by adding 2 means with a characteristic admittance to the load impedance, characteristic impedance to the load admittance, we just in order to get easily cancel, we just use here susceptance terms. So based upon this, the combination of the stub and the line will present a conductance which is equal to the characteristic conductance of the line. Right? Then based upon this, the stub should be placed as nearer to the load as possible so that the prevailing mismatch, if any, is for the minimum possible length. So if it is connected nearer to the load end only, we can easily neglect the reflections in the same medium. That's why the stub can be connected nearer to that of load impedance which is connected at the output side. Then coming to the mathematical analysis. So in order to analyze or in order to calculate stub length and the thickness of the stub, how much thickness it is needed to connect the parallel connection to that of main transmission line, we are going to analyze that one with respect to the mathematical equations. To write the mathematical equations first, see here Zn is equal to, what is this equation? The input impedance of a lossy transmission line. Why we can say that this is a lossy transmission line means Zin is equal to Z naught into ZL plus Z naught tan H gamma L by Z naught plus ZL tan H gamma L. As we know that gamma is exist in that particular case, gamma equal to alpha plus j beta equal to. So for a lossy transmission line, the propagation constant gamma can be given by in all the primary constants of a transmission line, and along with all the primary constants, the operating frequency of a transmission line is also mentioned as r plus j omega L into g plus j omega c root over. So in this case, see, gamma can be given by alpha plus j beta equal to root over r plus j omega L into g plus j omega c. Right? So here, if gamma is exist means alpha is also exist along with the phase constant beta. If alpha is exist means alpha is the notation for attenuation constant, there must be some attenuation in the line. So attenuation means that amplitude or some disturbance must be exist in the signal, hence it is represented with loss, hence the name has given for this as lossy transmission line input, lossy transmission line input impedance, right? So Zn is equal to Z naught into ZL plus Z naught tan H gamma L by Z naught plus ZL tan H gamma L, right? So this is the line equation, lossy transmission line input impedance with all the characteristic impedance and the load impedance, so including. So Zn is equal to Z naught into ZL plus Z naught tan H gamma L by Z naught plus ZL tan H gamma L. Okay. So here Z naught is the characteristic impedance and ZL be the load impedance, and where gamma is representing for the propagation constant and L be the length of the transmission line. So gamma equal to alpha plus j beta equal to root over, this is the term as given. So for a lossless transmission line means distortionless line case, we just assuming R equal to G equal to 0. The power dissipated elements means R and G are two power dissipated elements, where L and C are two energy storing elements. Hence, now to dissipate these two dissipation elements R and G must tending to 0. So if we substitute R and G by 0 in this equation, gamma can be equal to alpha plus j beta equal to root over j omega L into j omega C. If you substitute R and G by 0, then it becomes then j omega into root over LC. So if you observe, RHS part of this, which is becomes only imaginary. There is no real term. But in the LHS part of this will be real term is also exist. Now if you compare both sides, real and imaginary terms, the real term alpha is equal to 0 and the imaginary term beta equal to omega root over LC. So this is the case for a lossless transmission line, gamma can be given by J beta. Right? So now Zn is equal to Zn for lossy transmission line, the input impedance equation is given by Zn is equal to Z naught into ZL plus Z naught tan H gamma L by Z naught plus ZL tan H gamma L. Now from this equation, converting impedance into admittances. Now from this equation, if we substitute all the impedance terms by admittance terms, means see, Yin means Zn is equal to 1 by Yin and Z naught is equal to 1 by Y naught and ZL is equal to 1 by YL. Our reciprocal terms means Yin is equal to 1 by Zin, and from this Y naught equal to 1 by Z naught, and here YL equal to 1 by ZL. Right? So if you substitute Z naught, ZL and this Zin by Yin, Y naught and YL, then these are the terms. Means from this equation, if we convert all the impedance terms into admittance terms, then it becomes Zin by Yin and Z naught by Y naught into ZL by YL plus Z naught by Y naught, and here also Z naught by Y naught, and from this ZL by YL. Right? So then the admittance input admittance equation Yin is equal to y naught into yl plus y naught tan h gamma l by y naught plus yl tan h gamma l. Okay, so all here yn is representing input admittance, y naught is the output, characteristic admittance, and yl be the load admittance terms, and gamma be the propagation constant, which is including attenuation constant alpha and the phase constant beta, where L be the length of the transmission line. Now we are replacing all the terms, means y naught. If you take this y naught into this side, then y naught from this equation, yn is equal to y naught into yl plus y naught tan h gamma l by y naught plus yl tan h gamma l. In this, if you take this y naught into this side, yn by y naught is equal to yl plus y naught tan h gamma l by y naught plus yl tan h gamma l. Okay, so this can be given by here ys, and it is said to be normalized input impedance. So where normalized input impedance is given by, it is the ratio of the input admittance to the output characteristic admittance. So ys is equal to yn by y naught, and this is said to be normalized input admittance. Okay, now from that, so previously what we have, so yn is equal to, so from this equation yn is equal to, and if we take the ratio as ys is equal to, means if you replace yn by y naught by ys, which is equal to, and in the denominator and the numerator, if you take y naught as common, then see here yn means yn by y naught is equal to ys. This is ys equal to, and yl plus y naught tan h gamma l by y naught plus yl tan h gamma l. This is the equation, and where ys is said to be normalized input admittance, and which is equal to. Now we have to simplify this equation. If you take in the numerator as y naught as common, then yl by y naught plus tan h gamma l, and in the denominator also, if you take y naught as common, then 1 plus yl by y naught into tan h gamma l. This is normalized input impedance. So yn by y naught is equal to ys is equal to yl plus y naught tan h gamma l by y naught plus yl tan h gamma l. Now if you take in the numerator and denominator y naught as common, then in the numerator this term becomes yl by y naught plus, and this y naught gets cancelled, tan h gamma l is left out by, and in the denominator also, if you take y naught as common, 1 plus yl by y naught tan h gamma l. So in the numerator and denominator y naught gets cancelled, which is equal to, so from this how you can write yl by y naught plus tan h gamma l by 1 plus yl by y naught into tan h gamma l. So this can be written as here ys is equal to yl by y naught plus tan h gamma l by 1 plus yl by y naught tan h gamma l. And if we replace this yl by y naught in the previous equation by yr, where yr is said to be normalized load impedance or admittance, right? So if we replace yl by y naught as yr, then this becomes yr plus tan h gamma l by 1 plus yr tan h gamma l, nothing but ys equal to normalized input admittance equal to yr plus tan h gamma l by 1 plus yr tan h gamma l. So here yl by y naught is equal to, from this relation, and it is replaced by yr, where yr is given by normalized load admittance. And if you replace it with zr, that is said to be normalized load impedance. Now for high frequency lines, as the frequency is more, then alpha equal to 0. High frequency lines means For high frequency lines, omega is high or frequency components are high, then alpha equal to 0, gamma equal to j beta. As we have discussed in the previous, that is for a lossy transmission line, input impedance is equal to Z0 into ZL plus Z0 tan H gamma L by Z0 plus ZL tan H gamma L. For a lossless transmission line, we must assume here R equal to Z equal to 0, then alpha equal to 0, beta equal to omega root over LC. Now from this, gamma can be substituted by J beta, right? So now, if you substitute gamma by J beta and alpha by 0 in the previous equation, then it becomes Ys is equal to, now from this, if we replace YR plus tan h j beta L by 1 plus YR tan h j beta L, right? So as we know that the formula in the trigonometric formulas, that is tan h j beta L is equal to j tan beta L. According to the formula in the trigonometric formulas, then tan h j beta L is equal to j tan beta L, right? So if you replace tan h beta L by that formula, which is equal to, means how we can write this one, YR plus j tan beta L by 1 plus YR JYR tan beta L. See here, for high frequency lines, alpha is equal to 0, gamma equal to j beta, or for a lossless transmission line, then input impedance, that is normalized impedance, is given by here Ys is equal to YR plus j tan beta L by 1 plus YR tan beta L, where YR is the normalized load admittance. Okay, now in order to simplify those two equations, means in order to multiply these two, in order to find the real and imaginary terms, we just consider Ys. In the previous equation, what we have, Ys is equal to YR plus j tan beta L by 1 plus j YR tan beta L. So, and if we consider now here, in order to get the stub length L, we need to separate the real and imaginary terms. To get the to write the real and imaginary terms as separately, we just rationalize this equation with 1 minus j yr tan beta L by 1 minus j yr tan beta L. Right? Suppose if these two gets cancelled and the equation remains the previous statement, it won't alter. Right? So depending upon that, we can rationalize the term, the total term with this 1 minus j into yr tan beta L by 1 minus j into yr tan beta L, which is equal to, if you multiply these two, then in the denominator, if it looks like this one, 1 plus j into yr tan beta L into 1 minus j yr tan beta L. So it looks like a plus b into a minus b formula. So if the formula according to this is given by a minus b into a plus b equal to a square minus b square, is a simple formula in the algebraic equation. So a square is 1, in place of a here we have a, and in place of b JYR tan beta L, means 1 minus j into j becomes j square, and j square value is minus. In the formula itself we have minus, then minus of minus becomes plus, y into yr becomes yr square, and tan beta L into tan beta L becomes tan square beta L, and based upon these two relations, a plus b into a minus b, a plus b into a minus b. Okay, now if we multiply in the numerator part, then yr plus j tan beta L into 1 minus j yr tan beta L. Okay, so if you multiply, means these two, and upon expanding these two equations, ys is equal to, so yr into 1 becomes yr, then minus j, then yr into yr becomes yr square tan beta L, right, plus j tan beta L is multiplied with the rest of the two, means j tan beta L into 1 becomes j tan beta L plus, and here j into j becomes j square. Then if you multiply plus into minus minus, then according to j square its value is minus 1. Then minus of minus becomes plus. Then yr and tan beta L into tan beta L. Now tan square beta L by in the denominator 1 plus yr square tan beta L. See, upon expanding this one, yr is multiplied with first, means yr minus j yr square tan beta L, then plus j tan beta L, then j into j becomes j square, less into minus as minus, then j square value is minus 1 plus, then yr into tan means tan square beta L by in the denominator 1 plus yr square tan square beta L. Okay, so this is ys. Ys is equal to yr minus j yr square tan beta L plus j tan beta L plus yr into tan square beta L by 1 plus yr square tan square beta L. So this how we have been written based upon this is the formula. If you observe, these two are there in the denominator, means looks like a plus b into a minus b. If you apply the formula as a square minus b square, then in the denominator part becomes 1 plus yr square tan square beta L. Right? So now from this we can separate tan square terms and the rest of the two terms. Means yr into, means yr terms. If you consider yr terms and first and last two terms, means if we separate real and imaginary terms, means ys is equal to first and last two terms. If you take yr as common, 1 plus tan square beta L is left out. Then in the 2, if we take plus j as common, then 1 minus yr square is the common term. Then tan beta L is common between two. So between these two imaginary, j is the common, tan beta L is common, and then 2 becomes 1 minus yr square tan beta L by 1 plus yr square tan square beta L. Okay, so based upon the above equation, we can separate here. This is the part which is called as real, and this is the part which is called as imaginary. Right? So we can separate the real and imaginary terms based upon this equation. Real part is given by yr into 1 plus tan square beta L plus 1 minus yr square tan beta L. And then the denominator term is as usual, that is 1 plus yr square tan square beta L. Okay. So for no reflection, means we can consider yn is equal to y naught. See, previously what we have written, see, yl by y naught equal to yr, and in here y naught by yn by y naught equal to ys. According to the normalized input impedance, if you consider for no reflections case, input impedance is equal to characteristic impedance as y naught, means input admittance is equal to characteristic admittance. Yn is equal to, for no reflections case, input impedance Zin is equal to Z naught. Hence from the admittances, that is Yn is equal to y naught, or simply Yn by y naught equal to 1. Okay. Now according to this relation, and previously we have got ys is equal to normalized input impedance. Ys is equal to consisting of real and imaginary parts, where real part is yr into 1 plus tan square beta L. There is won't exist any imaginary part, and if we take in the imaginary terms as separately, plus j into 1 minus yr square tan beta L by 1 plus yr square tan square beta L. Okay. Now, thus the stub has to be located at a point where the real part of the input impedance is equal to the unity. To get the stub length, we just use here input impedance is equal to characteristic impedance, or input admittance is equal to, means Yin is equal to characteristic admittance as Y0, or if you consider the ratio as 2 becomes 1. Now from that we can consider only a real part of that. See, in the previous equation what we have, so Ys is equal to Yr into 1 plus tan square beta L plus j into 1 minus Yr square tan beta L by 1 plus Yr square tan square beta L. See here, Yr into 1 plus tan square beta L plus j into 1 minus Yr square tan beta L by 1 plus Yr square tan beta L. So to equate means if the stub has to be located at a particular point where real part of Yin must be equal to 1. So real part of this equation means we can consider only in the numerator part as this is equal to 1, then 1 equal to Yr into 1 plus tan square beta L by 1 plus Yr square tan square beta L, right? So Yr into 1 plus tan square beta L by 1 plus Yr square tan square beta L is equal to 1, right? So assume here L is equal to Ls, where Ls is said to be stub length. L is the notation for length and S stands for stub length. So in order to calculate stub length, we must equate real part of the input impedance to the 1. So consider only real part, and real part is given by here Yr into 1 plus tan square beta L by 1 plus Yr square tan square beta L. And if you replace L by Ls, then it becomes 1 is equal to Yr into 1 plus tan square beta Ls by 1 plus Yr square tan square beta Ls. Okay, so that is equation is given by Yr into 1 plus tan square beta Ls, means L is replaced by Ls here, and 1 plus Yr square tan square beta Ls is equal to 1. Now to write the equation for this Ls, see, cross multiplication between 2 means Yr into 1 plus tan square beta Ls equal to 1 into 1 plus Yr square tan square beta Ls. Now from this, if you separate the Yr terms and the tan square terms, now see, multiplication between these two becomes Yr plus Yr tan square beta Ls is equal to 1 plus Yr square tan square beta Ls. To write the equation for Ls, we can separate here tan square terms and the real terms. Then Yr minus 1 equal to, Yr is here, take this 1 into this side, then it becomes minus 1, which is equal to Yr square tan square beta Ls, Yr square tan square beta Ls minus Yr into tan square beta Ls. Okay, now from this Yr minus 1 equal to, in between this Yr is the common between 2 and tan square beta Ls is the common between 2, then here it will become Yr, means already we have taken Yr as common, then Yr into Yr becomes Yr square, the equation remains the previous one, then Yr minus 1, right? So both sides means, if we consider Yr into tan square beta Ls is equal to Yr minus 1 by Yr minus 1. So both gets cancelled, hence Yr tan square beta Ls equal to 1. So that can be written as here. See, from this, if you multiply these two, Yr into 1 as Yr, then Yr tan square beta Ls, then 1 plus Yr square tan square beta Ls. To write the equation for this stub length, we can separate tan square terms and the Yr terms. Hence, if you take this 1 into this side, Yr minus 1, which is equal to Yr, if you take the relation between, means common factors between 2, then Yr tan square beta Ls is common, then Yr minus 1 is to be left out. Now both sides, these two gets cancelled, or if you write like this also, there is no change in that equation. That is Yr tan square beta Ls equal to Yr minus 1 by Yr minus 1. both gets cancelled, which is equal to 1. Now from this, tan square beta ls is equal to 1 by yr. See, from this relation, tan square beta ls equal to 1 by yr. Okay. Now from this, tan beta ls equal to write the equation for ls, so here tan square beta is there. To cancel that square term, we just consider square root on both sides. Square root on both sides. Right? If you consider square root on both sides, then here root of tan square beta ls is equal to 1 by root of yr. So here square root gets cancelled, tan beta ls is equal to 1 by root yr. Okay. So in the previous analysis, the normalized load admittance yr is given by, what is that ratio? See here, yr is nothing but yl by y0, right? Load admittance to the characteristic admittance. So normalized load admittance yr is replaced by here yl to the y0, right? So if you replace that by, see, yr equal to yl by y0. Now from this, if you replace here, tan beta ls is equal to 1 by root yr, means root of yl by y0, which is equal to, in the denominator if you observe, the ratio is there in the denominator. If you consider it in the numerator part, then it becomes root of y0 by yl. So tan beta ls is equal to 1 by root over yr equal to, and yr is nothing but normalized load admittance, and yr is equal to yl by y0. Now if you substitute in place of yr by this relation, and the ratio will be in the denominator, if you consider it in the reverse order, then tan beta ls equal to root over y0 by yl. Okay. Now to calculate stub position length, means the stub position, generally the notation for length is given as L and S is for the stub. So stub length, to calculate that, previously what we have, tan beta ls is equal to root over y0 by yl. Tan beta ls equal to root of y0 by yl. Okay. So where y0 is the characteristic admittance and yl be the load admittance, where tan beta ls, beta be the propagation phase constant and ls be the stub length. Now from the previous analysis, tan beta ls is equal to root over y0 by yl. Now in order to calculate this ls, we just consider first beta ls is equal to, take this tan into this side, then it becomes tan inverse of root over y0 by yl. Or consider both sides on tan inverse term. See, consider this as the term, and tan inverse, if you multiply with the tan inverse on both sides, then we are going to get here, so tan inverse of tan beta ls equal to tan inverse of root over y0 by yl. So tan and tan inverse gets cancelled, then from this beta ls is equal to tan inverse of root over y0 by yl. Okay. Then from this, ls is equal to 1 by beta tan inverse of root over y0 by yl. Okay, where beta be the phase constant of the transmission line. So ls is equal to 1 by beta tan inverse of root over y0 by yl. See, beta ls is equal to tan inverse of, so beta ls is equal to tan inverse of root of y0 by yl. Now from this, ls is equal to 1 by beta tan inverse of root over y0 by yl, where y0 be the characteristic admittance and yl be the load admittance, and beta be the phase constant of the transmission line. ls is the stub positional length, and it is given by 1 by beta tan inverse of root of y0 by yl. Or sometimes if you replace y0 by 1 by z0 and yl by 1 by zl, means we want to express the stub position length in impedances, we just replace y0 by 1 by z0, yl by 1 by zl. Then from this, ls is equal to 1 by beta tan inverse of root of y naught means 1 by z naught by yl is 1 by zl. So which is equal to 1 by beta tan inverse of root over 1 by z naught into zl by 1. So from this ls is equal to 1 by beta tan inverse of zl by z naught. This is the stub positional length of a single stub matching. So the thickness part and the imaginary part equations, if you equate the imaginary part of that to the this thing, we are going to get normalized load admittance equations. So to calculate thickness and all, we will be equating the imaginary part to that of 1. Then from that we are going to get the stub positional thickness also. Okay. So from this, if you are going to equate the real part of normalized load, normalized source impedance to the unity, then from that we'll be getting the formula as the stub positional length in terms of admittances means ls is equal to 1 by beta tan inverse of root over y naught by il, and if you want to express the stub positional length in the impedances means ls is equal to 1 by beta tan inverse of root over zl by z naught, right? So this is the stub positional length of a single stub matching technique, right? The advantages and drawbacks which are to be or going to discuss in the next lectures. Okay, so now what we have learnt in this particular lecture is what is the main advantage of this stub matching. Then there are two cases of stub matching techniques are there: single stub matching and double stub matching. So we have been evaluated first impedance of a input impedance of a lossy transmission line. From that we have been evaluated for lossless transmission line input impedance. There the transmission length of line is L is replaced by LS, where LS stands for stub positional length. To calculate the stub positional length, we use the normalized source impedances and normalized load impedances. Now from that we have been calculated the stub positional length of a single stub matching, which is given by mathematically equation as ls is equal to 1 by beta tan inverse of root over y naught by yl, and ls equal to 1 by beta tan inverse of root over zl by z naught. Means if you want to express all stub positional length in terms of admittances, 1 by beta tan inverse of root of y naught by yl, and if you want to express that in terms of impedances, then ls is equal to 1 by beta tan inverse of root over zl by z naught, where zl is load impedance and z naught be the characteristic impedance, and similarly y naught is the characteristic admittance and yl be the load admittances, right? So in order to calculate stub positional length and thickness of a stub matching techniques, we used all the impedances by admittances in order to calculate mathematically easy way. We just replace all the impedances terms by admittances in this particular single stub matching techniques. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.